Hello and welcome to Honors Function. In this lecture, we're going to introduce the second member of this very important family of function, the logarithmic function. Again, let me repeat what I said at the beginning of this unit. Logarithms were introduced before exponentials, okay? For the longest time in history, people, I should say, mathematicians, people interested in mathematics rather, had some qualms about all sorts of numbers. Negative numbers for one. Negative numbers were not always accepted. Rational number for sure. Irrational number even more. Irrational number were not accepted for the longest time, okay? The 19th century finally gave them a full-fledged existence. So irrational exponent, let's not even go there, right? Logarithm, on the other hand, were introduced pretty early on in the 17th century by John Napier, and again, it is considered one of the very, very important discovery in mathematics. Now, though, especially in high school, when we cannot really introduce these topics with rigor, except in calculus, possibly, it is traditional to introduce exponential first and then present logarithm. So, what is a logarithm? Let's begin. So you remember the graph of an exponential function for which the base is above 1. It's an increasing function. Also, please, at this point, it's going to be fundamental, at least for a little bit, to recall my notation of exponential function. I say mine, but you may find this notation here and there, usually not in high school textbook though. You're gonna see that it makes sense. I need it in this very lecture. I don't need it anywhere else. So this is the exponential function with a base above 1. And one of the most important property, we've used it to solve equation, is the fact that this function is one-to-one. Now, what is the most important property of a one-to-one function? It has an inverse. Well, guys, here we are. By definition, the inverse, so I'm using the inverse function notation right here, the inverse of exponential is, by definition, logarithm base a. That's it. That's all. I could stop the lecture right here. I could stop the lecture right here and send you to do some problems. That's it. Finished. We know everything about inverse, right? Well, come on, let's apply a little bit some of the results here. It's kind of pretty interesting. Let's first look back at the three very important formula we wrote between a function and its inverse. So the first one was to say that if y equals f of x, if f brings x to y, then, and actually it's an if and only if, right? F brings x to y if and only if f inverse brings y to x. Okay? So, what does it mean in terms of exponential? Let's take this one and let's write what it means for an exponential. Y equals f of x, so that's y equals exp base a of x. If and only if exp base a inverse of y is equal to x. All right, now, what is x base a of x? Well, this is just a to the x, right? So y equals a to the x. And what is x base a inverse? By definition, it is logarithm. So that means log base a of y equals x. That is a very important property. You have to remember it. It's one of the defining property of logarithm, okay? The thing to remember is that the base is the same in both. The base is the same, and then input becomes output, output becomes input. All right, here's the first one. Second one, suppose x is thrown into f, and then we throw this f of x into f inverse. Do you remember what you find? You find x. You go back to x, right? The image that you have to keep in mind is this one, right? This is f of x. Well, actually, let me call that y right there. This is y, and this is f right here. And f minus 1 is the carrier that goes the other way. This one right there, right? So x goes to f of x, and f of x is thrown back to x. All right. So how does it work with exponential? So we have, right here, we have exponential inverse of exponential base a of x, right here, is supposed to be x. All right. So now, what is the exponential base a of x? Well, that is a to the x, right? And what is the exponential inverse base a? Well, that's a log base a. I guess I should use the same kind of a letter right here. Log base a. And that is x. And this is the second very important property between log and exponential. If inside of a log base a, you have an exponential base a, these two will cancel and you're back to the input. I sometimes will write this one as log base whatever of whatever to another power right here is that power, no matter what the power is, okay, no matter what that is. So you need to remember this one in its most general form, of course, okay? Don't get stuck to a and x, okay? It's a formula. Finally, the last one of the three most important property is if you take an x and you throw it inside f inverse, and then you throw that inside f, you will get back to x. It's exactly the same as the one we just saw. How does it work with exponential and log? So you have exponential base a of exponential inverse base a, and that is equal to x. The exponential inverse base a is the log base a of x, right? Now, how do you do an exponential base a? This is raising to a power, a raised to that power. Now that power is that, so this is a to the log base a of x, that is supposed to be x, okay? So here's the third very important property between log and exponential. Before we go over a few examples, let me tell you two things. First of all, in the first formula right here, this is often referred to as the exponential form, and this is the log form, okay? Two sides of the same coin, okay? These two forms are equivalent. We call that the exponential form, and that we call it the log form. The other thing I want to mention is something about this property right here. This property allows us to give another definition to the log base a of x that is completely equivalent to the first one, okay? The other definition is kind of interesting. Log base a of x, what it is, look at it. It's an exponent to which a must be raised in order to find x. Log base a of x is the exponent to which a must be raised in order to find x. Let me show you what I mean concretely right here. What is log base 5 of 3, for example? Well, it's the exponent to which 5 must be raised right here. It's the exponent. This is the exponent right here. You place it right there. 5 to that exponent is going to be equal to 3. Okay, so you realize that this exponent is probably not a rational number. Okay, so it's an exponent to which 5 must be raised to find 3. I like this definition. It's very workable. Let's go over some examples right now. Check this out. What is a log base 2 of 8? Well, log base 2 of 8 is the exponent to which 2 must be raised in order to find 8. 2 to the what equals 8? 3. That's it. Another way to do that is to try to write 8. So look, another way to do that is to try to write 8 as a base 2 exponential. Log base 2 of 2 cubed is equal to, well, that's 3. That's a second property. If the base of the log and the base of the exponential inside are the same, you just cancel each other, right? And you find the exponent right there. But I kind of like the first approach better. Let's go over the second example. Log base 2 of 2. So here, actually, in this one, I'll go with the, that's obviously 1, right? 2 is 2 to the 1. Therefore, these two will cancel together. That's 1. Log base 2 of 16. So 2 raised to what power equals 16? 2 to what power equals 16? 2 to the 4. Log base 2 of 0.5. 2 to what power equals 0.5? 2 to the negative 1. All right. Log base 2 of root 2. 2 to what power equals root 2? Okay, 2 raised 2 raised to what power is equal to root 2? Well, that's simply 2 to the 1/2, right? So this is 1/2. Log base 2 of 1 over 32. Okay, now I'm going to change my approach right here. I'm going to write 1 over 32 in base 2, okay? I'm just changing my approach. I'm going to use another formula. So it's 1 over 2 to the 5th. So it is 2 to the -5. So this is log base 2 of 2 to the -5. Therefore, it is, please, I'm crossing it out, but it ain't too pretty. Just don't cross it out here. Let's not do that anymore. -5. Et voilà. I'm going to let you do 7, 8, and 9. I was having a lot of fun here. I was just going along, but you need to do a little bit of work too. All right, write the other form of the expression. I'm going to do the first one. I'm going to let you do the last two. You need to figure out which one is the exponential, which one is the log right here, okay? It's pretty obvious. Please don't change any of the number. Don't change any of the number. Here's the exponent, okay? Therefore, the log, this is the exponential form, right? The log will have the same base. The base is 2. Then the output becomes the input, 0.5, and the input becomes the output. Here we go. That's it. These two forms are equivalent, okay? Again, I start with the base. All right, I'm going to let you do this one. Fine. This one you do need to change a little bit, okay? This is 25 to the 1/2, of course, equals 5. And now you write the log form. And here you're going to write the exponential form. Let's go over more problems. I really love these logs. All right, number 13. Log base 5 of 0.2. Okay, can I write 0.2 in base 5? Yes, you can. Start by writing the fraction corresponding to 0.2. You don't know it? Okay, fine. 0.2 is 2 over 10, right? Okay, simplify this. This is log base 5 of 1 over 5. Oh, okay, got it. Log base 5 of 5 to the -1. Here we go. Same bases, right? Base of the log and base of the exponential are the same. -1. I'm going to let you do 14. I'm going to do 15. This is actually a very important one. You need to remember it. So, a to what power equals 1? A to what power equals 1? 0. Okay, so it doesn't matter what the base is right here. The output of log base anything of 1 is always going to be 0. All right, let's finish with two sets of definition of very important bases and a few more examples and we'll be done. All right, the first one is the common logarithm. It's a logarithm that we use all the time in science. It's a logarithm base 10, okay? And the only reason why it's very common in science is because numbers are in base 10. Any numbers that you're writing is in base 10, okay? So this is a very useful logarithm. So we usually don't write log base 10 of x. Usually this is written log of x. Now, I'll talk to you in class about some kind of contradictory notations there in higher math. We'll talk about it briefly. We'll read something pretty funny about it. But for us, this is what we're going to do, okay? So before I go over some examples right there, let me write the three formula relating log and exponential. So the first one is what? Y equals log of x if and only if. Okay, so input becomes output, output becomes input. The base is 10. The base is 10. Input becomes output, output becomes input. 10 to the y equals x. That's the first one. Second one, log of 10 to whatever is equal to whatever. Third one, 10 to the power of log of whatever is equal to whatever. Here we go. All right. These are the three formula that we covered, apply to base 10 log. Finally, the most important base of all in math. I'll tell you in class why it's the most important, though you won't be able to necessarily understand it at this point, is the natural logarithm. What's a natural logarithm? It's a logarithm base e. Okay, now this is it. This is the most important in math. You need to know this one. Let's write the three formula. Oh, first of all, we don't write log base e. We write ln. Okay, we write ln. All right, so here we go. The first one is y equals ln x if and only if. What's the base? It's e, so e to the y equals x. Second one, ln of e to whatever equals whatever, and finally e to the power of ln of whatever equals that whatever right here. Okay, let's now do the last series of example and we'll call it a day. Alright, example 16. This is when it gets interesting because we get to use exponential and log here. Example 16, you gotta solve for x. Well, hey, come on. You see where it is right here. So what do? E to the 2x minus 1 equals 1/3. This is the exponential form. I'm writing the log form right away. 2x minus 1 equals ln of 1/3. It's an exponential base e, of course, right? So you solve that and you find x equals ln of 1/3 plus 1 over 2. That's the exact answer. I don't want to see an approximation of it. Let me give you another way to think about this step right here. I kind of like it. And students usually do too. Another way to look at this right here, e to the 2x minus 1 equals 1/3, and that's going to be a little bit clearer after the third lecture, is to think of it as applying the function ln on both sides. Ln on both sides, right here. And what is ln of e of x? Well, that's the other formula, right? The second one. These two cancel each other, and what you're left with is 2x minus 1 equals ln of 1/3. I kind of like this one because you can import into so many different models here. You apply a log on both sides. Please do 17. I'll do 18. What am I going to do? I'm going to move the 5, that's -3, and I'm going to divide by -2. So I have ln of x squared minus 1 equals 3/2, right here. So what do I do now? Now I will write the exponential form right here. So it is x squared minus 1, that's the input, it becomes the output, equals e, that's the base right here of the log, right? E to the 3/2, okay? And so you have x squared equals e to the 3/2 plus 1. Careful right here, I'm removing a square. So x equals plus or minus, right? Always e to the 3/2 plus 1. That's it. Now, again, another way to think of this is to take this equality, ln of x squared minus 1 equals 3/2, and to think that on both sides, you are applying the exponential function base e. Remember, we don't write the base right here. You are applying the exponential function base e. And x of ln, these two cancel each other, their inverse function, will give you x squared minus 1 equals e to the 3/2. So, of course, you're going back to the same thing. It's a slightly different way to do it. There is a teacher at Bullis who uses some kind of awful terminology here. Let me see. She says you exponentiate? I think she says you exponentiate both sides. My. What should I not hear? That means basically once you get this right here, you go like this. Okay? You just exponentiate both sides. Please let her know what I think of her terminology. I'll appreciate it. I'm kidding. She's a great teacher. All right. Last two. Nope, they're for you. Enjoy them. Thank you for watching.